This is my recording for my second research paper. The title of this paper is Enhancing Learning-Enabled Software Systems to Address Environmental Uncertainty. This paper looks into the issue of learning-enabled systems training data sufficiently when faced with environmental uncertainty. They look into finding new ways to get better training data with the goal of improving performance of a system. They aim to produce a tool that constructs new synthetic training and testing data that's used for the purpose of assessing a system's performance in uncertain environments, as well as improving the resilience of a system in the presence of uncertainty. The solution is crucial for systems that are cyber-physical, such as autonomous vehicles, because they must be tested against all environmental uncertainties. By utilizing machine learning, these systems become learning-enabled, and verification of expected behavior requires good test data, and this is essentially what this paper is trying to obtain. Cyber-physical systems have the risk of not being tested for all environmental uncertainties, and this is caused by gaps in testing data which lead to poor performance. Bridging the gap between training data and performance through self-adaptive tools will allow for enhancing performance under new environmental conditions. Although Enki does successfully generate synthetic test data, which is used to assess DNNs under environmental uncertainty, this is just an introduction to the topic. Enki is limited to DNNs and Cypher10 dataset, so future research needs to explore additional techniques as well as implementing it to be used on different services and strategies. DNNs are capable of learning feature relationships that are abstract. However, developers essentially have no direct control over how the information is understood within the hidden layers. And the hidden layers are shown in the image on the slide, as in the middle, this is where all the data is intermingled. And this can cause uncertainty because the outcome is difficult to evaluate. Deep neural networks, also known as DNNs, are a machine learning application that emulate complex systems. They process data from onboard sensors and they provide task assistance. An example of this is autonomous vehicles who have lane keeping. They essentially take in features as an input and output an informative label. They're trained to approximate target functions through the adjustment of weights within their hidden layers. And once the objective loss has been minimized through adjusting weights, and the objective loss is basically the error of a DNN's output and then the ground truth. So once this has been minimized, the training phase is complete, and the DNN is now able to understand relationships between features and make accurate outputs. DNNs are not as resilient and certain due to the gaps in training and the mystery of the hidden layers. So therefore, they require enhancing. The DNN can face the issue of showing accuracy, however, not actually generalizing data well when it's outside the training or test dataset. And this causes it to be superficial because, as stated by J. Joe et al.'s article about measuring the tendencies of CNNs to learn surface statistical regularities. Search-based testing is an automated method that aims to optimize test cases for verifying and validating your system. And this is done by exploring and researching a desired state. Types of search are random search. Test case candidates are randomly generated until the optimal set is found. There are also tools such as the Evo suite that use evolutionary algorithms, which require configuration of the test case representation. And then it implements crossover and mutation operations to preserve valid tests through generations of the iteration through the use of fitness heuristics. And this leads to search-based testing to evolve and find test cases relevant to the system. Novelty search diversifies each solution through comparing each candidate with its neighbor and choosing the one furthest from the nearest neighbor. This search algorithm is thoroughly explained in the article called Evolution Through the Search for Novelty, where it can basically find a range of solutions that cover a range of problem space, all of which do not have to be within the same local optima, and therefore covering a wider range of space. This has been implemented within INCI to find conditions that diversify specified sets of performance metrics, and it is kind of what helps it be so well. So they introduce an automated technique to find scenarios of environmental uncertainty that produce a wide range of behavior from a learning-enabled system. They focus on explicit internal logic rather than intermediate representations of control data that are often unclear. The challenge is selecting data that is good for testing. In this paper, an evolution-based technique is evaluated, which constructs new synthetic data for training and for testing. And this is achieved by generating many different environmental effects, then selecting ones that basically cause the most unique and extreme behaviors on the system. The use of parameterized transformation functions allow this to happen. INCI is a black box automation tool that they have developed, which essentially discovers diverse operating conditions for any general system under testing. They attempt to identify if INCI can identify gaps in the training that cause a learning-enabled system to perform poorly, and if INCI can be used to improve the resilience of a learning-enabled system to the effects of uncertain environmental conditions. The responsibility of INCI is to take a trained DNN and find the impact of environmental uncertainty on it. And the figure shown outlines the data flow within the INCI process, the figure on the slide. Where it implements an evolution-based search process, and then it evolves a population of individuals that each represent an environmental effect. Evolution is then used to modify characteristics of the environmental effect in a population to encourage diversity while considering the population's behavioral metrics. This paper focuses on image classification within the DNNs in environmental conditions that are not favorable, focusing on self-driving features. INCI has stemmed off of a similar approach, Loki, which integrates novelty search into its self-adaptive system. INCI, however, is a standalone system, and it's not limited to traditional code-based systems, as Loki is, and it also doesn't require a goal model to be defined for the software under the testing. Because of this, it provides flexibility and control over novelty computation, because it uses software under testing's behavior as the base for diversity. And then we can discover test cases that lead to different behavior. Current existing techniques for automatic test generation for DNNs are Deep Explore and Deep Test. However, they don't currently encourage diversity in regards to the DNN's performance. And this is how INCI differs from them, because INCI explicitly searches for operating conditions that lead to these unique system responses. INCI has better coverage of vulnerabilities because it's capable of discovering a broader range of test cases that can possibly reveal strengths and weakness behavior. Another benefit of INCI is the output it provides. So INCI's transformation is independent of its input. Therefore, we can expect more generalized patterns from the results, and this is useful because it allows the developer a range of conditions that they should target for different strategies. And then through the use of crossover and mutation operations, INCI maintains a diverse generation, and it continues to evolve through generations by reproducing those who have the best novelty score. And then INCI is terminated once the mean novelty score converges, resulting in a set of environmental conditions, or characteristics actually, that cause different behaviors in the target system. Simulation is then used to alter the Cypher 10 images to create synthetic images, allowing them to observe the classification error, activation coverage, and the activation pattern of the DNN. The original DNN is then evaluated against the results from Enki and the original unaltered test dataset from Cipher 10 to eliminate any bias, and performance is determined. This is an assessment of the impact of uncertain environmental conditions on their original DNN. So now they can take this result and improve the performance of the DNN by training an improved DNN by applying the transformation function to the original Cipher 10 training data with the parameters given by Enki. So through testing on raindrops, brightness, and contrast with Enki, deep test and random generation methods, they concluded that Enki could in fact successfully find specific environmental effects with greater different impacts on the DNN, and that from the output parameters they could successfully analyze which environmental effects are involved in each case. And this gets rid of the issue of with novelty search. Enki was able to actually find more adverse environmental effects and create a DNN that handled those effects through lowering accuracy in comparison to deep test and random generation methods. This paper's research needs to be expanded in regards to what models it has used in collaboration with. Currently, it not only works with DNNs that implement the ResNet architecture alongside the Cipher 10 dataset. It needs to be expanded in order for its effectiveness to have less variation and be useful in the real world. The current simulation tested a limited number of environmental factors which may behave differently in the real world, and they may be circumstantial. Enki has the potential to be expanded on and used in collaboration with other machine learning techniques, such as the ensemble method with subclassifiers, in order to execute alternate strategies of enhancing a learning-enabled software system.